Welcome back, my physics friends. Today we're going to look at a similar problem to one we saw before, where we have a projectile up on a cliff and we're going to see if we can hit the boat, except this time we're going to kick our projectile at an angle. And I'm going to say my angle here, let's just make it up. Let's say that I kick it at an angle of 42 degrees. Alright, so my very first thing I should do is say, well, let me draw my two-column given chart. And again, I'm going to have a column for the x and I'm going to have a column for the y, because the accelerations in the x direction and the accelerations in the y direction are different, and so they need to have their own kinematic equation to go along with it. And on that case, I know the acceleration in the x direction is 0 because there's no outside forces acting on the projectile in the x direction when it's in the air. And when it's in the air, the acceleration in the y direction is negative 9.8 meters per second squared due to gravity. All right, let's see what else I can fill in here. Well, I want to see how far my projectile lands, whether or not I'm going to hit the boat. So I'm going to claim that my initial S position in the x direction is 0 meters, and I eventually want to find that final S position here. And then in the y position, I'm going to say my final S position is 0, and then I'm starting 20 meters above. Again, you could say that you start at 0 meters, but then your final position would have to be a negative 20 because it's going to fall downward, and the negative indicates down. All right, and then remember, time is going to be the same in both columns, and I need my initial velocities. Well, it tells me the initial velocity is 15 meters per second, but that 15 meters per second, is it in the x direction, the y direction, or both? And in this case, because it's set at an angle of 42 degrees, this 42 degrees, that 15 meters per second, is in both the x direction and the y direction. It has a part that moves the projectile forward in the x direction, and we call that V0x, or the initial x direction. And then we have a part that moves the ball up or down, and we call that V0y, or the initial y velocity. Now, neither of those is 15, and in fact, I need to figure out what those pieces are. And so I'm going to do that over here. I'm going to draw a triangle, and I'm going to redraw my 15 meters per second here. And then I'm going to draw my x direction, V0x, and my y direction, V0y. And this is a right triangle, and I know that my angle here is 42 degrees. Okay. So I can use trig to help me figure out what my x piece and my y piece are. Okay. And so I can use, if I remember SOHCAHTOA, it tells me what trig functions to use. So S stands for sine, and it tells me that the sine of theta is equal to the opposite side over the hypotenuse. The cosine of the angle is equal to the adjacent side over the hypotenuse, and the tangent of the angle is equal to the opposite side over the adjacent. Okay? And so what I need is V0x. V0x is the side that's adjacent to the angle, it's next to the angle, which means I'm going to use cosine. Okay? So cosine of theta is going to equal the adjacent side, which is V0x, over the hypotenuse, which is 15. And so in order to get V initial by itself here, I need to multiply both sides by 15. And I'm left with V0x is equal to 15 times the cosine of 42 degrees. And if I use my calculator, make sure you're in degrees, not radians. 15 times the cosine of 42. That gives me 11.15 meters per second. Okay. And now I can put that here, 11.15 meters per second in the x direction. Okay. For initial velocity in the y direction, well, that side is opposite the angle, so I'm going to use sine. So I'm going to say, well, the sine of theta is equal to v0y over 15. And again, to get v0y by itself, I'm going to multiply both sides by 15 degrees. I'm sorry, but yep, by 15 meters per second. And then I'm left with v0y is equal to the sine of theta, or the sine of 42 degrees, times 15. And so that would be 15 times the sine of 42, and that gives me v0y is equal to 10 meters per second. Now I have that in my chart. Okay, so if I want to know where this projectile is going to land, I have to think about how it's going to travel. I know that it's pointed in this direction on the way up, so it's going to go up a little bit farther, and then I'm hoping that it will land somewhere within that 20 meters and hit the boat. Okay? So the first thing I should probably find is this time, so that I can eventually find this s in the x direction. Okay? I need to know which column to use. Remember, I need 4 variables. So I have 1, 2, 3, 4 in the y, and only 1, 2, 3 in the x. So let's look at the y column to find time. So with our 3 kinematic equations, I'll write them here at the top. We have v equals v naught plus at, s is equal to s naught plus v0t plus 1/2 at squared, and v squared is equal to v naught squared plus 2a delta s. So I'm going to use the s equals s naught equation to find time. So I have s is equal to s naught plus v0t plus 1/2 at squared, and I'm working in the y direction, and I'm trying to find time. So let's see here. Now I have s is 0, s naught is 20, plus v0, I'm sorry, what's v0? v0 is 10, plus 10 times t plus 1/2 negative 9.8 t squared. Uh-oh, I have a t squared and I have a t. That can present a problem, but if you look carefully, maybe you remember what that looks like from math class. That's a quadratic. I have a square term and a single term and a constant. And that's pretty easy for me to solve. I'm going to show you how to do it graphically. It's the fastest and the easiest way to do one of these problems. So let's set this up so it looks more familiar. 1/2 times negative 9.8, that's negative 4.9 t squared, plus 10t plus 20 equals 0. Okay. And now I'm going to come over here to my calculator, my graphing calculator, and I'm going to go to y equals, and I'm going to, in y equals 1 here, I'm going to enter the equation. Okay. So I'm going to enter negative 4.9 x squared plus 10x plus 20, and then I'm going to graph it. And I can see here I have 2 places where I have zeros, where my line crosses the time axis. And one is negative and one is positive. These indicate what the time is. Well, time can never be negative, so I'm actually interested in the positive root here. And so I can use the calc function, which is above the trace key. If I hit second calc, and then number 2, and I'm going to solve for the 0. It asks here for left bound, so I'm going to scroll my cursor over. Oh, there it goes. Until I see that the cursor is to the left of the 0. I'm going to hit enter. And then it's going to ask for a right bound. So I'm going to move my cursor forward to the right. So it's to the right of the 0. And then I'm going to hit enter. And then it asks to guess. So I'm going to move it closest to 0 as I can get it and hit enter again. So I get 3.28. Okay, so we solve for our positive 0, and we get a time here of 3.28 or 3.3 seconds. Okay, so my time is 3.3 seconds. Okay, and now I can put that up in my chart. And now I have enough information in my x direction to solve for my final position. So I'm going to use the s equals s naught equation again, but this time in the x direction. S is equal to s naught plus v0t plus 1/2 a t squared. And remember, the acceleration in the x direction is 0, so this whole term here, this gets drawn to 0 because anything times 0 is 0. As well as my initial position is 0, so I'm going to make that 0. So my equation turns into s is equal to v0 times t. And s then is equal to 11.15 times the time, which is 3.3 meters. And so when I do that multiplication, I get 11.15 times 3.3. Oh, sorry, this is not meters, this is seconds. I get 36.8. So s is equal to 36.8 meters. Now, how does that compare to 20? Well, it's bigger than 20 meters, so I missed the boat yet again. Okay? I missed the boat yet again. Okay? So that's how you could find how far out a projectile would go, and sometimes we refer to that as the range. Okay? Let's also talk about its landing velocity, so what speed it hits the ground or the water at. Okay? So if this is my projectile, it's going to continue to have the same initial velocity all the way across because the acceleration in the x direction is 0. So the final x velocity is also 11.15. So Vx is 11.15 meters. But it's also moving down at that point. And so the y velocity at that point, I don't know what it is. I can't claim that it's the same as the initial, because that's only true at a symmetrical height in the parabola. So at this point here, the Vy is the same as the initial, but it fell through this extra distance. So I need to find out what this final Vy is. And I can do that with probably the easiest kinematic equation, that first one here, V equals V naught plus AT. Okay? So if I have V is equal to V naught plus AT, V is what I'm looking for. My initial velocity in the y direction is 10 plus negative 9.8 times the time, which is 3.3 seconds. And so I get negative 9.8 times 3.3, and so I have 10 here plus a negative 32.34. And I'm left with a final velocity in the y direction of negative 22.3 meters per second. And that makes sense because it's moving down. Okay, so this is negative 22.3 meters per second. But remember, the actual overall final velocity is this hypotenuse of the triangle here. Okay? And the angle associated with it is this. So I can use Pythagorean theorem to find out what that final velocity is. So I'm going to do a squared plus b squared equals c squared. And so I have 11.15 squared plus negative 22.3 squared is equal to c squared. Uh, 11.15 squared plus 22.3 squared, and then take the square root of that. So I get V final is equal to 24.9 meters per second. And then I'm going to use the inverse tangent again, like we did in the first one, of 22.3 over 11.15, and that would give you the angle.